Feigenbaum's work shows us that chaos, though infinitely complicated in its details, has certain simple, universal features. New York Times reporter James Gleick, in his very readable book titled Chaos, tells us why universality is important.
Universality made the difference between beautiful and useful. The physical implication was that real-world systems would behave in the same recognizable way, and that furthermore it would be measurably the same. Feigenbaum's universality was not just qualitative, it was quantitative, not just structural, but metrical. It extended not just to patterns, but to precise numbers.
Lorenz, Feigenbaum, Mandelbrot, and others have used computers to discover a whole new realm of bizarre and beautiful mathematics. And mathematicians have continued trying to tame this mathematics with theorems and proofs in the traditional manner. As a consequence, our understanding of dynamics and of determinism itself has been transformed. Classical determinism is now believed to be too rigid to reflect reality, except under certain limited conditions where reality behaves in a smooth, linear, and therefore predictable way. These are the circumstances in which data can be extrapolated, that is, predicted based on the continuation of current trends. The great 17th century philosopher and mathematician Gottfried Wilhelm Leibniz long ago tried to justify extrapolation by postulating that an all-knowing God could calculate with infinite precision. With or without Leibniz's God, most physicists today continue to believe that mathematical results can be extrapolated or broadened across a wide variety of conditions. But Stangers and Prigogine believe that such results can be extrapolated only in simple dynamic systems.
Dynamics has discovered today that as soon as a dynamic system to be described is no longer completely simple, the determinist description cannot be realized. There are dynamic systems of different sorts. There are the rare ones, in which determinism exists as a limit state, costly but conceivable, in which extrapolation is possible between the approximate description of any observer and the infinitely precise one of which Leibniz's God is capable. And there are systems in which the idea of determinist prediction conflicts with the laws of dynamics, and in which the idea of determining the initial conditions becomes unthinkable.
Catherine Hales, who was trained as a chemist but who later became a professor of literature, says more generally that the discovery of chaos changes our vision of the world.
The world as chaotics envision it is rich in unpredictable evolutions, full of complex forms and turbulent flows, characterized by nonlinear relations between causes and effects, and fractured into multiple-length scales that make globalization precarious. The difference between the two paradigms is expressed by the icons often associated with them. Whereas the Newtonians focused on the clock as an appropriate image for the world, chaos theorists are apt to choose the waterfall. The clock is ordered, predictable, regular, and mechanically precise. The waterfall is turbulent, unpredictable, irregular, and infinitely varying in form. The change is not in how the world actually is. Neither clocks nor waterfalls are anything new, but in how it is seen. The broadest implications of chaotics derive from this change in vision.
Chaotic behavior is a surprising, counterintuitive mathematical phenomenon that describes many real-world situations. Chaos has revolutionized our philosophical ideas about determinism and predictability. But the mathematics of the transition to chaos, from the simple and predictable to the chaotic and unpredictable, also leads us into territory largely unknown to traditional science. Science in the Newtonian tradition deals essentially with the behavior of existing objects and systems. It does not normally ask how or why objects come into existence. But questions of origin are perhaps the most fundamental we can ask, and often the most interesting. How does a violent hurricane generate itself in the calm tropical atmosphere? How does something as complicated as a human being arise from a union of two cells in the womb? How does a new species appear? And how does life itself originate? Until recently, scientists have largely avoided these sorts of questions. In some fields, like chemistry and especially biology, it obviously was hard to avoid them altogether. So it's not surprising that chemists and biologists are the ones leading us away from the Newtonian view of the world. Ilya Prigogine, a Russian-born Belgian chemist, has simultaneously held chairs at both the Free University of Brussels and the University of Texas. He is perhaps most responsible for this transformation in science because of his fundamental theoretical work in the area where physics and chemistry meet. Prigogine showed that under the right conditions, matter has unexpected properties that let it organize itself into complicated structures. These properties are the key to understanding questions of how natural organization begins. Prigogine was awarded the Nobel Prize in 1977, and the implications of his work are far-reaching. His large, multidisciplinary team of scientists has pursued these implications into fields as diverse as biology, psychology, and economics.